All right, so I want to talk about something called polarization. If I had a rope attached to the wall over there, if I went like this, you know, the rope, you know, it would look like this, right? And when we talked about waves some time ago, we said this was called a transverse wave. And why is it called a transverse wave? Well, because the wave, you know, the disturbance, right? The wave pulse goes that way or that way. But like if I take some spray paint and sprayed a dot on the rope, what would the rope do? What, you know, with that spot, what would that spot on the rope do? It would go up and down. So, you know, the disturbance is going this way or this way, but the rope itself, a piece of the rope itself, goes this way. So that's transverse to that, right? That's transverse wave. If I had a spring on a table and I just push it like that, that would be a longitudinal wave, because you know, the spring itself is going like this and the wave pulse is going like that. So like sound, that's a transverse wave, you know. I mean, longitudinal wave. Okay, why do we care about that? Well, again, let's say that this is the rope. So I'm doing it like this, right? And so, I mean, it really looks like this. So this plane, the plane of the whiteboard, that's called the polarization plane. You know, I mean, you know, I'm doing it like this, right? I'm oscillating or I'm moving the rope like this. So this is the plane of polarization. If I move the rope like this, that would be the plane of polarization. Okay, that's a big deal, right? Okay, why do we care? Well, so anytime you have a transverse wave, you're going to have a polarization plane, right? That sort of makes sense, okay? Now here's the question, all right? So this is a picture, well, not a, whatever. This is supposed to be a representation of an electromagnetic wave, okay? And you can see that there's two pieces, right? There's the electric field piece in the red, and there's a magnetic field piece in the blue. And see, that's why we're lazy, right? We call it an electromagnetic wave. Electricity, magnetism, because there's both, you know, electromagnetic wave. All right, so, you know, the prediction is that this thing is polarized, right? There has to be a plane of polarization. So there's a plane of polarization for the E part, and there's a plane of polarization for the B part, okay? So, you know, it looks like a transverse wave, right? Well, how do you prove it? You do an experiment. What else? Okay, so here's the experiment. Okay, so let's just concentrate on the electric field, all right? The electric field. We could have done the magnetic, doesn't really matter. So, okay. So this is just regular, ordinary light. So it's called unpolarized light, just light from the sun, you know, or something. Okay, the electric field of unpolarized light oscillates randomly in all directions. That kind of makes sense, right? So these are just the electric field, right? Okay, so these are just supposed to represent the directions of the electric field. So, you know, this is that way, that's a plane of polarization, that's plane of polarization, and so forth. It's just, you know, ordinary light that hasn't been filtered or hasn't been changed in any way. Just ordinary, regular light, right? Unpolarized light, random oscillations. Okay, then we have this thing called Polaroid. You've heard of the Polaroid camera? Okay, so this is something that somebody, what do you want to call it, discovered, invented, I don't know. Anyway, this is a sheet of Polaroid. What does it do? Well, it has polymers, you know, parallel to each other. And you can see that it blocks some of the light. So let's read it. So only the component of the electric field perpendicular to the polymer molecules is transmitted. How come? Well, because the other ones are absorbed by the polymer molecules, all right? So all of the light is absorbed except for the light where the direction is perpendicular to the polymer. Okay? So there you go, right? Polaroid sunglasses, you know, what do? You know, they block off most of the light, right? Ta-da. Okay. All right. So that's that. Okay, so let's see. So basically, so you know, if you shine unpolarized light through a Polaroid sheet, the intensity, the brightness is going to get less. It's going to decrease, right? Because you're blocking everything except for this one, you know? Okay, so, all right. So that kind of makes sense, right? Okay, now, all right, so one sheet of Polaroid will decrease the intensity of the light. No kidding. Now here's the question though. What if we have two sheets of Polaroid? Okay, two sheets of Polaroid. All right? And let's say that the transmission axis of this guy is perpendicular to the transmission axis of that guy. So what I'm saying is, so here, all right, so this one only allows this through. What if we have another sheet that's rotated 90 degrees? What's going to get through that? Nothing. Agreed? Nothing. So there you go. Okay, so so you know, people did experiments, and everything that was predicted for transverse waves was shown to be correct for light. So people concluded correctly that light is a transverse wave. They did it separately for electric fields and magnetic fields. Okay? All right, so here are some of the rules that people developed. Okay, so if light goes through a single sheet of Polaroid, the intensity of the light that's transmitted is the initial intensity divided by 2. That's all. So just intensity divided by 2. Okay? So like I said, you have unpolarized light hitting a sheet of Polaroid, and then what do you get? You get polarized light, right? And the intensity is just half of what it was initially. Now, let's say we have multiple polarizers, which is the fun stuff. So now we have multiple polarizers. So now, this is the rule number 2. The transmitted intensity is the initial intensity divided by cosine squared theta. What's theta? Theta, oh brother, it's supposed to be a theta there. Theta is the angle between the transmission axes. So now theta would be 90, right? Okay, so this is what you mean. So anyway, that's the formula, okay? So you have unpolarized light going through a polarizer, then you have polarized light that goes through another polarizer, and it's still polarized light, right? I mean, right? But the funny thing is they call this I0 the polarized light. So this is the light that's already gone through the first polarizer. And this is I0 cosine squared theta. So again, if you have crossed polarizers like that, then the angle between this and this is 90 degrees. Cosine of 90 is 0. And so according to this formula, the intensity transmitted is whatever that is times 0. And of course, I have a demonstration which I forgot. So next time I'll show you, if I remember. All right. Okay, now I'm just going to do just a few random things that you'll find in the book. Let's say you're studying climate change, greenhouse effect and all that. So of course, what's important then is, you know, where does the energy come from that hits the Earth? Obviously from the sun, right? So the electromagnetic waves, right, from the sun hit the Earth. And, you know, you have to calculate the intensity of the light, and then you got to figure out how it warms up the Earth and all that kind of stuff. So these are just some formulas. We're not going to spend a lot of time on them, but here they are. Okay, so intensity. I've talked about intensity before, right? I also say it was like brightness. Well, there's a formula for it, you know. So, and we had it before when we talked about waves. So intensity is the power, right? Power, that means energy over time, divided by the cross-sectional area. Okay, so for example, you know, if you just have a regular cheapy flashlight, and you shine it on the whiteboard, you might have this big circle, right, where the light spreads out. And so it's going to be low intensity. On the other hand, if you have a laser, you shine it to the whiteboard, you just see this little tiny dot. And so A is going to be smaller than from the regular cheapy flashlight, so the intensity is going to be much, much larger, right? So, they use lasers to burn things and to weld things and to, do surgery and all that kind of stuff because you get high intensity beams. Okay, so intensity is power over area. Now you just have these formulas. Don't spend a lot of time on them. But, these are electromagnetic waves, right? And so power, again, is energy over time. Well, where's the energy come from? From the waves, right? And so this is speed of light, epsilon 0. This is an electric field. This is the magnitude of the electric field, wave squared over 2. And then you can get in terms of magnetic field. Don't get all excited about it. If you have a point source, and we talked about this before too. Let's say I have a point source of radiation or sound or whatever, right? Just a small source of radiation or something like that. Then, again, intensity is power over area. But, if it's a point source and it's transmitting in every direction, these are spheres, right? These are spheres. And what's the cross section? What's the area, the surface area of a sphere? 4 pi r squared. So this basically is proportional to p over the distance squared. That's actually useful. Use that in medicine. Like if you have a patient with a radioactive source inside his or her body, then the intensity is power over r squared. Okay, so that's that. I just want to show you that. Now let's talk about something else. Oh yeah, there it is. Wow, much better picture than I drew over there, right? Okay, so this is for a point source, right? And there's the area. Okay, that's that. Okay, one last thing. Let's talk about photons, this is usually covered in a chapter on quantum physics, which we haven't talked about yet. But for whatever reason, Randy Knight put it in this chapter. So we'll just mention it, and we'll talk about it later. But it's just like a first mention, okay? All right, so we talked about light a lot in this semester. We talked about the ray model of light, where we learned how to do those ray diagrams. And then we talked about the wave model of light, right? Double slit experiment, diffraction, and all that kind of thing. Well, there's a third model. It's called the photon model. And again, we'll discuss it in gory detail later on. Okay? All right, so what does the photon model say? The photon model says light is made of massless photons. These photons travel in straight lines at the speed of light, c, in a vacuum. All right? Also, the photon model says that the energy of a photon, E, that's energy now, not electric field, right? The energy of a photon equals hf. F is the frequency. H is a constant. It's a constant. It's super, super tiny. And what does super tiny mean? All right, so we have E equals hf. So H is 6.63 times 10 minus 34 joules seconds. Now, if that's not tiny, I don't know what is, right? 10 to the minus 34. Okay, so, forget about the formula. Just think about it. Light is made of these tiny, tiny massless photons. And the energy is like incredibly small, right? I mean, we're never going to be able to measure, well, I better be careful. Okay, I mean, that's super, super small. We can measure it, by the way. All right, we can measure that. All right, so there you go. Now, why do we need another model? Well, we started off with the ray model. Maybe we didn't start off with that, but we started off with the wave model. And why did we use that? Because we saw interference effects when we did the double slit experiment. But we also know that light travels in straight lines through like mirrors and lenses, right? So sometimes we use that, right? It depends on the setup of the experiment. Why do we have to have a third model? Because experiments disagreed with this and this. So in certain circumstances, you have to have the photon model. Sorry. Okay, so let's just do some examples. Okay, so this is super, super low intensity light. And you can see, you can detect each photon as a speck, right? So this is some kind of a, a screen or something that's detecting these photons. So these are individual photons. And you can actually detect them. And you use something called a photomultiplier tube to detect these single photons. I have some in my lab, all right? So they work, They detect single photons. Now think about it. This is incredible because the energy is almost nothing. But yet these things can detect a single photon, okay? So, wow, that's awesome, right? Okay, so they act like little particles. Yeah? So that's incredible, But it gets worse, right? Okay, so they act like single particles, so you might think, sort of like the Ray model, right? Single particles. But watch. So now what we're going to do, remember that? So this is the wave interference picture that we studied in gory detail, So now what we want to do, we want to do the double slit experiment with light. We're going to do it with really, really low intensity light, really, really dim light. Now, come on. If you do the double slit experiment with water or electrons, you get an interference pattern, right? So the question is, what are we going to see with light? But then you say, wait a second. You just told me that light acts like particles. If light acts like particles and you do the double slit experiment, you shouldn't see an interference pattern, right? The wave's going to, here, let's look at it. There's a screen. There's the double slit. Here's a source of light. If it acts like particles, bright spot, dark everywhere else, right? Well, let's see. That's the beauty of physics. You just keep doing experiments. You learn things. Sometimes you learn your common sense is wrong. Okay, so that's what you see, right? With photomultiplier tubes. Light acts like single particles, photons, photons. So now we're going to do double slit, all right? We're doing this experiment, double slit, super dim light. So at the beginning, what do you see? You see particles of light, photons. But it's kind of interesting. They're kind of spread out. But there's no interference pattern, You just see these photons. So you say, okay, whatever. Then you just wait a little longer. You get more photons, right? I don't see any interference pattern, do you? Just wait a little longer. Still looks like a mess to me. Wait a little longer. Uh-oh. What are you beginning to see? I start to see some interference pattern. Wait a little longer. Can't you see these bright lines, dark lines, interference pattern maybe? Whoa! Wait a little longer, you see an interference pattern. Interference pattern. All right, this is after a very, very long time. Now, I hope you appreciate how crazy this is. Photons are individual, what do you want to call it, pieces of quanta of energy, right? We detect these with a photomultiplier tube. But when we shoot these photons through a double slit experiment and we wait a long time, what do we get? Wave interference. So light is acting like a photon and a wave. Now, if that doesn't blow your mind, I don't know what will, because that's crazy, but that's nature, all right? That's how it actually works. Okay, here's another cool thing that shows you how crazy nature is. This is called the single photon experiment. Done in 1992, long time ago, Okay, here's a single molecule. Okay, the light from the molecule emits one photon. Okay, one Creme photon. All right, so the light from a single photon emission in source S travels over two widely separated paths and interferes with itself at detector D after being recombined by the beam splitter B. What? Okay, remember, photons act like particles and they act like waves. Prove it! Here, this molecule emits one photon. Now, if you just think of that, you'd say, well, you know, you can go this way or this way. But what happens is that the photon acts like a wave. So it goes this way and that way. And then these are mirrors, and then they're reflected here, and they're reflected here. And you can change the distance of the paths. And so sometimes you get constructive interference, sometimes you get destructive interference. Now, how in the world can you get constructive interference and destructive interference if the photon acts like a single particle? You can't, right? Because single particles either go this way or that way. But again, the light acts like a wave, so it goes this way and that way, and then it recombines here. And depending on the path length, you get constructive interference and destructive interference. Wow, is that weird or what? So we'll talk more about that later when we do quantum mechanics. Okay, last just little thing. Let's talk about something called thermal radiation. This is just, you know, thermal means heat, right? And so you think of atoms in a substance, you know, they're always moving around, right? Okay, so atoms are always moving around, and therefore they have some, you know, thermal energy, right? Or you can say kinetic energy, thermal energy. Remember we talked about this a long time ago? If you have a can of paint in a hardware store and you ask them to shake it, you know, so you don't have to stir it as much, what happens to the temperature of the paint? It increases a little bit, right? Okay. All right, so here, look at this. So the numbers represent the temperature. So what do you notice? You know that the color depends on the temperature, right? You know? So low temperature, you get this red, you know, this red, kind of dim. And then high temperature, it's brighter, you know. Okay, great. Now, whoopee, right? Well, this is actually explained by, it's called Wien's law, okay? Wien's law, this is it. So here, you're plotting the wavelength of light. Here you're plotting the intensity of light, okay? And you know, here, this is, just look at it. So like from the sun, for example, you know, we see mostly visible light, right? And so there's the wavelengths of visible light and the peak, right? So look at, there's not a whole lot of light. There's not a lot of visible light here, right? There's a lot up here. I mean, this is temperature, okay? So you don't have a lot of light right over here at this wavelength. You have a whole bunch of light at this temperature and so forth. So this just gives you, this is just the equation that describes that, all right? Okay, so again, peak intensity shifts to shorter wavelengths as the temperature increases. So, okay, so if you have a really cold star, let's say, right, 3500 K, then it's not going to be very bright, right? The intensity is low. You're going to have your peak with longer wavelengths. If you have a hotter star, all right, it's going to be brighter than the cold star, and the peak is going to be shorter wavelengths. That's what it says. So there's the equation, all right? And you've got to be careful when you use the equation because look at the crazy units. Nanometers, all right? Nanometers, you know, not meters, nanometers. Kelvin, right? Kelvin from chemistry, and the temperature has to be in Kelvin. So if you do biology and astronomy, you'll use that again. All right, okay. Here's what we learned. Understand the circumstances under which changing magnetic fields lead to induced currents, right? You have a changing magnetic flux, you get an induced EMF. If it's a conductor, you get an induced current. Understand how the movement of a conductor through a magnetic field leads to a motional EMF. Yeah, we talked about that motional EMF two different ways. We learned about Lenz's law. We learned about Faraday's law. We talked about electromagnetic waves, right? Light, you know, when you accelerate a charged object, you get changing electric fields, which produce changing magnetic fields, which produce changing electric fields, which produce changing magnetic fields, and on and on and on, you know. And so you get a disturbance that travels through these electromagnetic fields. It travels at the speed of light. And then we learned a little bit about photons, but we'll do that later. Don't worry too much now. And then some other stuff. I don't want to talk about that. And that's it. Thank you very much.